Hello everyone, welcome to a new lecture in the series of Deep Learning for Control. In this lecture, we will be discussing approximation capabilities of neural networks, and the theoretical results in this direction are called as universal approximation theorems. Here is the overview of this lecture. We will start with a brief introduction to universal approximation theorems or UATs. Then we discuss a few preliminary concepts in this direction and some of the initial theorems from function approximation which are related to UATs. Then we explore the UATs in arbitrary width direction and also in arbitrary depth direction. Finally, we discuss a few extensions of UATs for other versions of the neural networks. As we have already said, UATs are theoretical results on the approximation capabilities of neural networks. UATs initially explored for feedforward neural networks, and after the introduction of different deep learning architectures, these are extended in other deep learning models as well. Two of the main directions of UATs are for arbitrary width neural network and for arbitrary depth neural network. In the case of arbitrary width neural network, typically studies it for a neural network with one hidden layer. The width or the number of neurons in this hidden layer can be arbitrary. This is the commonly used structure, and this particular structure can also be called as a shallow neural network. In the case of arbitrary depth, the depth can be arbitrary and the width is bounded. So here we have a neural network with the width equal to 1. We have only one neuron per layer. And this particular structure is not commonly used because of its limited approximation capability. In linear algebra, we have studied about basis. In general, basis is a set of vectors that spans all the other vectors in the vector space, which means all the vectors in the vector space can be represented as a linear combination of the basis vectors. Now, if we consider the set of continuous functions or its subset like the set of periodic functions, etc., we can have different basis functions such as impulse functions, sinusoidal functions, polynomial functions, exponential functions, etc. The universal approximation theorem states that any continuous function can be approximately represented in terms of linear combinations of artificial neurons. This implies the artificial neurons or the neuron function can be considered as a basis function, which is more like a data-driven basis function. Since this linear combination of neurons can only approximate a given function, and since neurons may not be linearly independent always, it may not be an actual basis in a linear algebra sense. But still, this is one way of looking at the universal approximation theorems. Next, we move on to the predecessors of UATs, which are the preliminary theorems from function approximation. We are all familiar with the Taylor series, which is one of the initial results in approximation theory. Taylor series says that any continuous real-valued function f of x, which is k times differentiable at a, can be represented as in equation 1, where we can approximate the function using a polynomial function, where the CI are the constants, which are derivatives of the function evaluated at that particular point. Here, this k times differentiable means that the function is sufficiently smooth enough. And a special case of the Taylor series is with the point a equal to 0, which simplifies this equation to this one. And this is basically a polynomial sum, which we can see. The Taylor series gives justification for polynomial regression methods. It says that polynomial functions can approximate any sufficiently smooth continuous functions. Next, another result is the Fourier series, which studies the approximation of the sinusoidal functions. And it says that any continuous and periodic function can be expressed as a sum of sinusoids as in equation 3, where A is the amplitude and phi A is the phase of the ith harmonic component, and T is the period of the function. It basically means that any periodic function we can represent as a sum of sinusoidal functions. Here, each of these individual terms in the summation can be called as a harmonic term or ith harmonic term. And for simple and smooth periodic functions, the Fourier series can be a finite sum. Whereas in the case of complex and non-smooth periodic functions such as sawtooth function, square function, etc., the Fourier series contains infinite number of terms. When it comes to non-periodic functions, the summation becomes an integral and the Fourier series becomes the Fourier transform. Another important theoretical result is the Weierstrass approximation theorem, which is an extension of the Taylor's theorem to arbitrary continuous functions. And it says that any continuous real valued function in a finite interval can be approximated with a polynomial function with a finite degree n, such that the approximation error will be bounded by epsilon for an arbitrary small epsilon. Next, we can move on to the representation theorem, which is proposed by Kolmogorov and Arnold. And this theorem says that any continuous multivariate function from a bounded domain to R can be represented as a summation of functions of this form. And all these theorems says that continuous functions can be represented as sum of other similar functions. That is the basic idea of this function approximation theory. For example, in Taylor series, these similar functions were polynomial functions. And in Fourier series, these were sinusoidal functions, and so on. And when we look at neural network, like the shallow neural network example, which we studied in the previous lecture, we were considering summation of ReLU functions. And we have seen that as we are increasing the number of ReLU functions, the approximation capability of the neural network were increasing. And this leads us to the UAT direction in arbitrary width, where we can consider a similar example from the previous lecture. Here we have a fold at 2, and here we have a fold at -3. If we sum these two functions, we get a function like this, where initially we have a fold at -3, and then we have also a fold at 2. And when we consider a weighted sum of 3 ReLU functions, we got another fold at here. So this implies that as we are increasing the number of neurons, the number of folds of this function increases, which means like we can have more complex nonlinear behavior. This is one of the theorem which is that if the function folds at h hyperplanes defined by this linear equation, then the number of linear pieces will be given by the summation of all these combinations. One of the initial version of UATs is in the arbitrary width direction, which says that any continuous function in a compact set can be approximated using a neural network of this kind of structure. This structure we have seen in the previous lecture as well, and this is structure of a shallow neural network. And for any continuous function, there exists such a neural network such that the difference is bounded by epsilon. This is the central idea of this particular theorem. And these initial results were based on sigmoid activation function. Later on, these were extended for other activation functions as well. This is the extension of the same theorem for non-polynomial activation function, which says that if sigma is any non-polynomial function, then summation of this kind of form can approximate any continuous function. And later on, other activation functions were introduced, such as ReLU become popular in 2000s, and Bhutan hyperbolic, etc. And for all these cases, the universal approximation theorems are proved. Now we move on to UAT in the direction of arbitrary depth. As an example, we can consider a neural network with 1 neuron per layer and a ReLU activation. So here for the first function, it is ReLU of 0x plus 5. So this is like a horizontal line with the y-intercept as 5. And ReLU 2x plus 4, we have 1 fold. And if we consider the composition of ReLU of 2x plus 4 with the ReLU of minus 0.5x plus 5, we get a function with the 2 fold. Now here we have considered a composition of 3 ReLU function. Here also we have only 2 folds. If we studied this further, you can see that if we are reducing more and more compositions or like more and more layers, the complexity cannot be increased. So the function will at max can have 2 folds. Means like if we have only width 1 or like 1 neuron per layer, we cannot approximate all the real valued function. And these results were generalized for functions from the set Rn. If we consider functions from Rn to R, and if the width of the ReLU network is less than or equal to n, then we cannot approximate all the functions in that set. Which means the minimum width should be greater than n for the real valued function containing n variables. And people will study the properties for minimum width for approximating functions from Rn to R. And this particular work studies that the minimum width should be less than or equal to n plus 4. And there was another recent research which says that the minimum width for universal approximation of Lebesgue integrable function is the maximum of n plus 1 or m. We should need at least n plus 1 or m number of neurons based on whichever is the largest. If m is less than n, then the minimum width is basically n plus 1. Here we will consider a few numerical examples to illustrate the neural networks and its approximation capabilities. In the previous lecture, we have seen the ReLU activation function, and similarly we can have other functions such as modulus function, step function, signum function, etc., for which the definitions are given here. Now we can also plot the graph of all these functions. Here we will plotting the graph of this function by defining each of these individual functions. And we can see the graph of each of these functions in this figure, where we can observe that the ReLU, modulus, step, etc. are piecewise linear functions, whereas sigmoid, swish, tanh, etc. are smooth continuous functions. Now we can consider some examples of neural network with arbitrary width. Here we consider a neural network with one hidden layer and arbitrary width as shown in this figure. And these are some examples where we have an example with one neuron, two neurons, and three neurons. Here with one neuron, we obtain one fold at the line. And if we take some of these two neurons, we got a piecewise linear curve as shown in this figure where we have two folds. When we taken the sum of three neurons, we got a piecewise linear curve with three folds as shown in this figure. If we see a shallow neural network, it is basically a weighted sum of neurons. And for each individual neuron, we can have a piecewise linear curves like this. And therefore, the basis functions for shallow neural networks will be the functions of this kind of form, where we can adjust the folding point or like these points and the slope of these linear pieces by adjusting the weights and biases of the neuron. Here we repeat this with different other activation functions as well. In this first case, we are taking the number of neurons in the hidden layer or the width of neural network as 3. And with that case, we can have different functions such as with ReLU, we obtained a piecewise linear curve as shown in this figure. With modulus, the functions will be like this. And we can see for other functions as well. Now, if we increase the number of neurons, let's say if we increase this number of neurons to 100 and selecting the weights and biases randomly, then in that case, we obtain the curve as shown in this, where we obtained a highly nonlinear curve, particularly in the case of step and signum. And here, as we increase the number of neurons, we can see that the curve becomes more and more nonlinear. Now we can consider the examples of neural networks with arbitrary depth. Here we are considering a neural network with one neuron per layer and arbitrary depth. We start with the examples with a single neuron and a composition of two neurons and a composition of three neurons. In each of these cases, we can see the plot as shown in this figure. Here with one neuron, we can have at max one fold in the line. And if we take a composition of two neurons, we got a folded line with two folds. And here also with three neurons as well, we got a folded line with two folds only. Now let's say if we increase the number of layers to 3. And in this case, we obtained nonlinear curves we can observe here. Now let's say if we increase the number of layers into 100, we can observe that we got a straight line. Here we obtained a straight line in the case of all the activation functions. So this indicates that in the case of width 1 neural networks, as we increase the number of layers, it does not increase the complexity of the nonlinear curve. Further, as we are increasing the number of layers, it mostly becomes a straight line. Therefore, in the case of deep neural networks, we require the width of the neural network to be sufficiently large in order to have approximation capability. So far, we have considered UATs for feedforward neural network. Recently, after the introduction of other versions of neural networks, UATs were extended for these networks as well. For example, the UATs for RusNet is studied in these two papers. UATs for Kolmogorov NN is studied in this particular paper. And UATs for convolutional NN is studied in this paper. Similarly, UATs for recurrent neural network or RNN is studied in this particular paper. And UATs for state-space neural network is studied in this paper. And UATs for neural ODE is studied in this paper. and the UATs for transformer networks are also recently studied. This means that universal approximation theorems can be extended for different versions of the deep learning model. It basically gives the theoretical guarantee on the approximation capability of deep learning models. That leads us to the end of this lecture. Thanks for watching.